Good evening, everyone. My young friends, school children from in and around Roorkee, teachers, principals, my colleagues here, our students, IIT Roorkee students, Professor T. Pradeep, who is Institute Chair Professor at IIT Madras, who is also chief guest of this function, Professor Ajit K. Chaturvedi, Director IIT Roorkee, and all others. I welcome you all to this function, this year's Science Day function. I'm Apurva, Dean of Academic Affairs, IIT Roorkee. So on behalf of IIT Roorkee and on my own behalf, I welcome you all to this function. Each year, February 28 is celebrated as a Science Day, National Science Day. Since 1988, our country has been celebrating this. And this is an auspicious day, a very significant day on which Sir C.V. Raman has discovered his Raman effect in the year 1928. It's another 4 years to be another 8 years for 1 century. And then subsequently in the year 1930, he was awarded Nobel Prize for Physics. Just let me share just one thing about Sir C.V. Raman. It is said that I have read somewhere, said that he has booked his voyage ticket, that steamer ticket to Swedish capital at that time to take part in the Nobel laureate function, Nobel awarding function, before the Nobel Prize was announced. Such was the confidence of this scientist. We are grateful to be part of this country which gave birth to such a kind of scientist. And this year's National Science Day theme is Integrated Approach in Science and Technology for Sustainable Future. And on this occasion, we have with us Professor T. Pradeep, who has contributed significantly in this area. He is the chief guest of today's function. May I request Professor C.N. Ramachandran to introduce Professor Pradeep. Please, Ramachandran.
Thank you, Professor Sharma. Good afternoon, everyone. On the occasion of this Science Day in the 175th year of our institute, it is my pleasure to introduce the chief guest of today's function, Padma Shri Professor T. Pradeep. Professor Pradeep is an institute professor of IIT Madras, a professor of chemistry and Deepak Parikh Institute chair professor. He is an alumnus of University of Calicut, IIT Bangalore, UC Berkeley and Purdue University. His research interests are in molecular and nanoscale materials, and he develops instrumentation for such studies. He is an author of more than 500 scientific journal papers and is an inventor of 125 patents and patent applications. In addition to the work on advanced materials, he is involved in the development of affordable technologies for drinking water purification, and some of them have been commercialized. His pesticide removal technology is estimated to have reached about 10 million people. Along with his associates, he has incubated 6 companies and 3 of them have production units. His arsenic removal technology, approved for national implementation, is delivering arsenic-free water to about 1 million people every day. The nation conferred Padma Shri on him in 2020. He is the winner of the World Academy of Sciences Prize in Chemistry and also the recipient of Nikkei Asia Prize 2020. He is a recipient of several other awards, including the Shanti Swarup Bhatnagar Prize, B.M. Birla Science Prize, J.C. Bose National Fellowship, National Award for Nanoscience and Nanotechnology, India Nanotech Innovation Award, and National Water Award. He also received the Lifetime Achievement Research Award of IIT Madras and the Distinguished Alumnus Award of IIT Bangalore. Professor Pradeep is a fellow of all 3 Science Academies of India, Indian National Academy of Engineering, Royal Society of Chemistry, the World Academy of Sciences, and American Association for the Advancement of Science. He is a distinguished professor He's a distinguished professor in a few institutions in India and is also the graduate faculty of Purdue University. He is on the editorial board of several reputed journals of the publishing groups such as Nature, ACS, and RSC. He is an associate editor of ACS Sustainable Chemistry and Engineering. Apart from his introductory and advanced textbooks on nanoscience and nanotechnology, he has also authored popular science books in Malayalam and is a recipient of Kerala Sahitya Akademi Award for Knowledge Literature. As part of his philanthropic activities, he supports a school in his village where 500 students are on rolls. With this introduction, I request Professor Pradeep to deliver his talk on science, technology, and innovation for sustainable clean water. Professor Pradeep, please. Thank you.
What a pleasure. What a pleasure to be part of this great institution celebration of the National Science Day. Apurva, am I audible?
You are audible, sir.
Yeah. Indeed, a great privilege and to be part of this function. Science to me is my blood, is my everyday activity. So as many of you, I celebrate science every day, and I am part of that celebration. And for those of you who are young, like Apurva said, school students are here, you will someday feel that science is part of your blood. And I wish you all the very best to feel that way, to be part of science, to be part of that excitement. For this invitation, I'm grateful to the director, Ajit Chaturvedi, and an IIT Madras alumnus, Apurva Kumar Sharma. I chose to talk about science, technology, and innovation on sustainable clean water. And that topic obviously is so vast, just as water is. But water is very small, this molecule. And I have been working with this molecule right from my PhD time. Those days, it was a triatomic molecule and its fascination for the chemical bond and how this chemical bond is sort of curiously concealing many of its complex problems, many of its complex properties. This is what I was fascinated about for a long time. But at some point in time, about 22, 23 years ago, I started asking this question, can that science be of some value to people? And that has taken me science of sustainable clean water. And I'm going to briefly illustrate that story to you and to show you pointers on this day looking into the future. And looking at that future, we must realize that we are alone in this huge, vast universe. This is this so-called great environmental picture ever taken. This is called the Earthrise. This picture was taken on December 24th, 1968, by the Apollo 8 astronaut William Andrews. As he was in this vessel, looking at the rising Earth in the background of the moon, this picture was taken. And as you see that isolated planet, the beautiful planet. This planet was photographed many times subsequently. Another very important picture in this context is this pale blue dot picture taken by Voyager 1. As Voyager was just going beyond the solar system, passing Uranus, it looked back the Mother Earth and took this beautiful picture. And what you see is this blue dot. That blue is nothing but water. Earth is nothing but water. And this is that very important message. Earth just has that water from itself and no water coming from elsewhere. And obviously, water is the most important inheritance of our planet. People talked about water coming from elsewhere, like this great man, Arrhenius, talked about this in his fantastic book, 1908. He talked about the possibility of life from other planets. But today we know that there is very little of water that comes to Earth from other planetary systems from the space. Although some amount of exchange of molecules happen and some interstellar dust comes into the Earth, but very little of water. And therefore, the amount of water on this planet is constant. So the truth is, well, on a subject such as water, one can talk about it for ages. But one may say that water is the essence of this planet. And water is the simplest and simultaneously the most complex problem of humanity. And one may say that every economic, social, and cultural outcome that we have produced can all be traced to water. Where there is water, there is wealth. Where there is no water, there is poverty. Where there is water, there is education. Where there is water, there is clothing. Where there is water, there is industrialization, many others. Everything, therefore, simplifies to water in a mega planetary scale. And in fact, there is water in everything that we do, including this lecture. There is water in electricity, there is water in internet, water in everything that we talk about. So that water, simultaneously, it is complex and simple, as I just said. It's also two sides of water that you see in this picture, the drought or the floods, or the scarcity of or its abundance. Water that way is quite a contrast. One thing, as you keep thinking about water, you realize that solutions for water lie in materials. All our water itself is a material. Solution for water is also a material. So while I was thinking about this lecture, I thought, what would be the kind of most appropriate picture that I should put on this statement? And I chose this. You know, in 1865, when Jules Verne wrote this fantastic book, From the Earth to the Moon, Jules Verne was talking about sending man to moon. And sending man to moon, obviously, the right kind of rocket has to be chosen. The right material had to be chosen. Verne chose aluminum. And you know, aluminum was discovered only in 1825, and aluminum was sort of produced a little bit in 1856. Aluminum had to wait some more years really to start commercial production in 1889. But Jules Verne wrote about the use of aluminum in this solar in this vessel. Well, it's a fantastic story, and obviously it has inspired subsequent missions. But it is important to realize that materials solved many important problems. Today, we have 1 kilowatt solar panel at 35 to 45,000. I'm only talking about panel alone, possible today because of materials. We have a 150 ampere hour rechargeable battery to charge the power that you produce with this solar panel. You need about 19,000 rupees. Both of these became possible I'm taking two examples with advanced materials. Seawater desalination for a cubic meter of water today is about 2.4 kilowatt hour, or about 45 to 50 rupees. So something like 2.4 units is what you need. Looking into the future, the green hydrogen-driven seawater desalination could make probably water at 1 paisa per liter. And that not in a very distant future, by 2030. Some of you might be surprised, but many may have heard these stories. But let me illustrate this with some numbers. You know, as a chemist, it is hydrogen plus oxygen giving you water. And that per mole of hydrogen, you produce 286,000 joules of energy. And 1 kg of solar hydrogen today is about 600 rupees. And it could be 150 rupees soon. This 1 kg of hydrogen can produce 143 million joules of electricity. So if 2.4 kilowatt hour is what is 1 cubic meter, 1 kg of hydrogen can make 16.56 cubic meter of water. And if I take this many cubic meters, well, rupees per cubic meter, 0.9 paisa per liter is the cost, just the energy cost. And obviously, you have to include other aspects such as energy efficiency for converting thermal energy to heat and transportation and plant costs and many others. But nevertheless, world is looking into that future. I will come back to this at the end of this lecture. So while that water I talked about is a beautiful picture of the world, the truth is that water cycle has been net zero for a long time. And I don't have to take this message to Roorkee, where people have done fantastic work on that cycle for a long time. But we have opened that cycle. Well, looking at the world outside, water plus carbon dioxide giving you sugar plus oxygen is the world. And it's going back, sugar plus oxygen going back to water plus carbon dioxide. The cycle has been closed. So if I were to look at the amount of carbon dioxide that is needed for humans and animals to live on this planet, that's about 29 billion tons of CO2 per year. But what has happened is that we have produced so much more that we are producing 258 billion tons of CO2. It is not that we are producing just sugar and oxygen. We are producing alkaloids and terpenes and many others and fats and all that, oils, apart from sugar and oxygen. And all of them are getting burned too. In addition, we are also burning petroleum, which ultimately is nothing but a conversion of carbohydrate to some other form. But we have opened the cycle. So the cycle people talk about in great detail in the climate context, but it has a very important water connotation too. The water connotation is that the amount of water is conserved. And therefore, if you wish to provide water for all, equitable distribution of water, you need to look at the world very differently. And this has been said many times, and in our country, Gandhi said this far more strongly than anyone else. Our earth, the air, the land, and the water are not an inheritance from our forefathers, but on loan from our children. So we have to hand over to them, at least as it was handed over to us. And there are several related statements you can find from Gandhi. There are several others, including our great chemist, Linus Pauling, who took this even further to say that life is a relationship among molecules and not a property of any molecule. It is important to hand over this property, this relationship, this mutual respect to our children. And therefore, water has been intensely studied. And water is intensely studied even today in many fundamental contexts. I took two examples from last year's literature to say that somebody discovered elastic ice towards the end of 2021. And somebody found metallicity on the surface of water. And all of these are beautiful experiments. And that is to tell you that so much more is there to discover in water. So to get you started, water is big. Water has we have huge precipitation. We have a huge per capita availability. We have a reasonable rainfall, far better than many other countries. And so water, therefore, is big. But at the same time, that big is its gaps, its opportunities, the wealth that is needed to create opportunities, wealth that is needed to make water equitable. And when you do all that, there is enormous satisfaction. And if you start looking at this problem in the global context, that's what I will do in the next 10 minutes or so, getting into something closer to India at a later point. Looking at water withdrawals, obviously, our technologies have been hungry for water. So therefore, those who use water, those use technologies intensely, they of course consume water. And as you can see, world is that way divided. But from the next picture, you will soon see water per capita withdrawals are very high in those developed nations. You see that water stress is not in those nations. Water stress, water risk, water inequality, that is somewhere else. So these countries are water rich and they consume a lot of water, but there is no water risk. These consume far less water, but they are enormously risked by water. And there are many reasons associated with it. And we will have no time to go into this. So if you want to talk about an American way of life for the whole world, that is going to require a completely different technology or technologies. And the way we look at technologies also have to be different. The risk is focused in certain areas, certain regions of the world. And if I take this risk further, and if we discuss this in a global context, you realize that one has to look at not really water withdrawals in a nation, you have to look at water footprint. And that looks at both production and consumption, and therefore global production today is a reality, and therefore water that is being produced elsewhere is consumed elsewhere because consumption is global, production is also global, water is what is moving across, and all of these virtual water trade has been a great subject of discussion over the years. So if you want to have an equitable water distribution across the world, you need to also consider water footprint. If you consider all of these, what you come to realize is that water and sanitation and inequality, they are so complex. But if you want to cut a total water infrastructure value for a connected global population of 9 billion people by 2050 or so, that would amount to a very large number of $60 trillion. And you ask this question, do we have it? And people have computed this and found that only 36% of the African population and 44% of the Asian population will be connected to a sewer network by 2050. Meaning the investment needed on this is so large. Now, these numbers may not look all that clear till you look at, or the implications may not look all that clear till you look at the total global production. So India's real wealth is estimated to be close to about $13 trillion. Wealth of US is about $130 trillion. So you can imagine what a sewer network really costs for a developed, so-called developed world looking at sustainable development goals and beyond. And that is the reason to look at that larger water issue in the form of various different heads. And you look at no poverty or zero hunger or good well-being, good health and well-being or quality education or gender equality or clean water or affordable energy or decent work or industry innovation, and all of these, you see an embedded water in all of them. And looking at from that larger global picture to realities in India, all of us are aware of those realities. And so therefore, let me not dwell into that. This is to only say that opportunities in water are plenty, whether we look at drinking water or sanitation, or whether we look at sewage, or whether we look at big W, stormwater, or many others. Opportunities are plenty. In drinking water, we continue to do well globally in the developed areas, but availability of clean water in many parts of the country is still an issue. But despite all that, India is doing well. And I got this data from Jal Jeevan Mission. There's one more recent data which I could not include. And that is to say that we are giving a very good functional household tap connection. And that is nearly 100% in several states, and other states are gradually getting there. Why is it that we have not been getting there, despite the fact that we have been getting this much of water? Well, it is so pathetic to see that every river is contaminated. And I was so shocked to see that 50% of the microbial diversity is lost in one river that we are monitoring in southern Kerala, southern Tamil Nadu. And globally, 83% of the freshwater species have declined. And this is what the journal Science says. And that is to say that a few more years, we will be the only species living on the planet. And that problem is obvious to all of us, that this is Yamuna. And this is also obvious to us that in the past few years, how groundwater has declined. But this brings a very important thought that can we continue to extract water or continue to deplete the groundwater sources and continue to increase GDP? I took this picture from this very important PNAS paper of Peter Gleich, who introduced this concept of peak water. So every nation goes through this peak of production. This is in the context of oil. America peaked oil production somewhere around 1974-75 period and started declining. And he asked this question, can there be something called peak water? Obviously, there is a peak water that you can sustain production at peak only for certain years. You can have sustainable production only at another level, what recharge allows. Looking at that, there is certainly a maximum to clean water, freshwater withdrawal. America peaked that freshwater withdrawal at this level, about 600 cubic kilometers per year. And although it sort of peaked that at that level for a long time, since 1975 or so, GDP continues to increase. This obviously means that new technologies are very much needed to create continuous wealth while packing the freshwater withdrawal at certain levels. This is certainly needed for our country. Now, obviously, we have a country which gets a lot of water. We have plenty of precipitation. It is never small. A city like Chennai, we get plenty of rainwater. It continues to be good, about 1,400 millimeters every year. In the past few years, it has gone up, but we continue to get. But still, we have water problems. So obviously, you see that water is not just a technology problem, it is also a management problem. In these next few minutes, let me talk to you about what water technologies we have done. In the past few years, many technologies have come globally. We introduced nanomaterials in the context of clean water. I've been saying that affordable clean water is a problem of advanced materials. On the surface of our planet, we have alumina or silica or all of these such minerals, and they have very low solubility product, and that allows you to have clean water at home. But civilization has produced a lot more materials, and these materials have a very high solubility product, and everything eventually ends up in water. And this has been a problem of clean water. And to address this, you have had new adsorbents, new sensors, new catalysts, new phenomena, and several new devices. And collectively, all of these make something called aqua nanotechnology, if the materials you are referring to are nanomaterials. So what has happened in the very recent past in the nanomaterial science for clean water is that materials have become atomically precise. What does that mean? If you take a small particle of a gold, here is a 25 atom gold protected with ligands, 18 of them. Today, you can synthesize in a laboratory. Many people in your chemistry department do this. And you can put it into a mass spectrometer or advanced instruments and measure its mass. 7390.5718 is the mass that you see. So it's called a high resolution mass spectrum. This is to say that it is possible to have precise composition. And that also means precise structure. This also means its properties can be precisely investigated. So we chose to investigate the properties of many materials with extreme precision as they interact with contaminants in water. This has given us a lot of surprises, a lot of new materials. Ultimately, this has given us products. We found that it is possible to create materials which can interact with arsenic, and not just two forms of arsenic, arsenite and arsenate, almost at the same efficiency, so that you have arsenic-free water. And this interaction happens very efficiently. Ultimately, you could put it in the form of a product or a filter. This is one of those very early things that we did. You take a region like Nadia district in West Bengal, and this boy is pumping water from a well that's about 60 to 80 feet deep. This boy is in a single stroke of this cast iron pump, which is 40 years old. He draws about 30 ml of 300 ml of water. And this water falls on the cement platform, and you see that it is red in color because of the iron oxide stain. And in this region, if there is iron oxide stain, it is also possible that there is some amount of arsenic. And you come back and look at it, you find that it is about 60 parts per billion, or 6 times larger or higher than the limits. And people have been using this, and this is something that we know for a very long time. This, in India, is known for about 60 years, and this is globally known for about 108 years. What we did was that we introduced these materials in the form of a filter without any pressure drop, no delay. The boy gets the same 300 ml of water in 2 seconds. And so during interval times in a school, the entire school can get clean water. And therefore, it has been implemented across. The basis of all these is, as I said, advanced materials. And what we thought about, or what we introduced, was a kind of material we called water positive materials. Now, looking at water technologies, you find that there are a number of materials. And these materials are typically made in water. In the course of their production, you contaminate water. In the course of utilizing these materials for clean water, of course, you create clean water. But after their life, they go back to soil and they again contaminate water. So you ask the entire water cycle, in their life cycle, what is the amount of water that it has produced? Oftentimes that number is not substantial. So here we have 1 liter of water used for its production. You create 500 or 1,000 liters of water, or 100 or 1,000 times water positive materials. The basis of such technologies is to create porous materials, pass water through, and selectively remove whatever contaminants that you like or you wish to. You engineer them. In a specific example, you create materials which are polymers, biopolymers. An example would be chitosan. Another example would be cellulose. Another example would be banana silk. So several of these materials, they're all typically water soluble. And in these materials, you add inorganic ingredients to create nanostructures. These nanostructures are deposited on these polymeric templates in the course of your reaction that is done in water at room temperature. You deposit tiny flakes of these nanoparticles, about 50 nanometers long, 50 nanometers wide, and about 15 nanometers thin. So this is almost like a sheet. This sheet will keep depositing on the surface in such a way that there is one sheet up, one sheet down, one sheet on the sidewise, another sheet on the other side. So you create a box like a matchbox. And in these matchboxes, you have typically about 15 nanometers wide cavities, and you can put nanoparticles. And you see these in the TEM. So these are sheets, a two-dimensional projection. These are nanoparticles that you see. You start from soluble ingredients, and finally you create a sand-like composite where you see water that is standing above. The sand, you can take it to civil engineering department and test its characteristics. You find that this is like the Young's modulus is similar to that of river sand. Now, what is so great about it? So let us say in these holes, you put silver nanoparticles. Silver releases silver ions, everybody knows that, and these silver ions are antimicrobial is also known. However, if you put real silver particles in water, after 3 days, you don't see silver ions in water. That is because in real water, you have silicate ions and calcium ions. They form calcium silicate generally on the surface of silver nanoparticles and creating tiny layers. Of course, this what I am just telling you is one-line sentence, but it has taken 3 years for me to study that thin layer. Now, you deposit these tiny layers because it is very difficult to characterize them. You see that silver ion concentration goes down normally, but in our case, it doesn't because silicate ions don't get into these holes, the nanoscale structures that we talk about. So as a result, this continues to release at 50 parts per billion, which is an effective antimicrobial concentration. And you run in this laboratory, you don't run it for 10 liters or 20 liters, you run it for 1,500 liters or 10,000 liters. In this particular one single sentence, I have embedded a whole lot of story here to say that laboratory has become a commercial place of production and testing. Otherwise, you don't test 10,000 liters of water in a chemistry laboratory. So that ion kills bacteria from a live bacteria, and they go dead. So obviously you ask this question, do you have nanoparticle toxicity? You don't release nanoparticles and there is no nanoparticle toxicity. How do you know that? You put nanoparticles deliberately and you see that bacteria pick up these nanoparticles, and individual nanobacteria, you can see nanoparticles in them. You can do spectroscopy of these. However, if you put the silver ions that are releasing, bacteria dying, you see lysis, that you see this bacterial membrane is all broken. You don't see silver nanoparticles. So this was the example of silver, but then there can be many other materials. In this particular case, we see iron oxyhydroxide, about 3 nanometers wide iron oxyhydroxide, specifically what is called two-line ferrihydride. You see 2 lines in the XRD. This is almost like an amorphous material. And what is so great about this amorphous metastable material confined in the nanoscale cages of the biopolymers, a bit of a detail, is to say that you can interact arsenic 3+ and arsenic 5+ effectively. Here we use Raman spectroscopy. This is arsenite, arsenic 3+, and this is arsenate, which is arsenic 5+. They interact with these iron oxyhydroxide, giving you some specific structures. These structures allow us to understand how this arsenite sit on the surfaces. And these will then allow us to engineer or so-called design this material so that maximum of these surfaces are present. Using such adsorption models, you can calculate the theoretical capacity of this. So it is quite high. About 12 to 20 milligrams of this material you take and make a small cartridge. And you make water with 100 parts per billion arsenite and 100 parts per billion arsenate. You pass it through and you get 2 parts per billion of in output water. You run it for over 1,200 liters and you get the break-even point. You say that this material is pretty good for such large capacities. Obviously, then you can make filters. So in a typical plant in the field, This is what you see in an affected area, supplying water to about 2,300 people. The plant is situated in a 40 cents of land area with towers as big as this. Now, because of these huge capacities that we have, you can shrink this to 6 inches of towers, adsorption columns or filtration columns. The whole thing is sitting in less than 3 cents of land area, quite attractive. Those days, we were implementing this in plastic containers, accepting these pressure vessels. Today, we implement it across. And I must have told you here that the capacity of this plant is 200,000 liters per day, or 20,000 liters per hour. Typically, you run for 10 hours. And here is again the same, almost the same capacity, 18,000 liters per hour, running to 200,000 liters per day. Concentration is about that. And this is what the output concentration is. Even today, we monitor this plant and after 8 years. So we are implementing this. This kind of implementations go on. So today, these plants are not, they are cast iron. They are built elsewhere and assembled at in the field. So this is what you see in the case of iron and arsenic removal plants in several parts of the country today. This particular example is from Punjab. The price at this point in time, when I started affordable water, I said that it should be 5 paisa per liter or better or lower. So today it is at 2.1 paisa per liter. And this is how, looking at all the costs, that works out. It's also possible to put all of these into sensor platforms. So we developed several sensors and then put them along with, and some of them commercial as well. So I have this brief movie, 1 minute, to show you. Unfortunately, the sound is not going to come to you. So when there is water which is contaminated, we can, of course, clean it by material technologies of this kind. If there is no water, we introduced atmospheric water harvesting using nanomaterials. So this is a spray. It's an electrospray made from a small tip of 50 microns in diameter. And what you see is an electrospray plume. And this has droplets. And these droplets can be used to create nanostructures like these nanowires. These nanowires look very similar to grass. The grass collects water when the temperature is below the dew point. And you can have a technology on a surface. You can have such nanostructures, and you can draw air to that. The humidity condenses on it if the temperature is below the dew point, and you can collect water. So we have products in the field, starting from 35 liters per day to 2,000 liters per day. So all these are great, and people have written extensively about all of these and our people in various technologies, including this one. But that was about active water harvesting input, energy input. But how about passive? With solar energy, with advanced materials of this kind, you could absorb humidity in the nighttime and release that humidity in the daytime by absorption of solar heat into a container wherein the humidity goes up. And because the humidity goes up, there will be condensation because the humidity goes beyond the dew point humidity. You collect that water. Advanced materials are needed there, and several of them are today being developed. In several other regions, we have salinity. Especially in the saline coastal regions, we have seawater intrusion, and water is brackish. We introduce capacitive deionization in several cases. Although this is a known technology, old technology, it is based on advanced materials. Because of the absence of advanced materials, these are really not cost effective, or these have not been cost effective. So here is a positively charged electrode, and you put materials on them which selectively absorb or electro-absorb or adsorb negatively charged ions. And the negatively charged electrode takes up the positively charged ions. So this electro-adsorption saturates. And at that point in time, this electrode is not delivering clean water, or electrode assembly is not delivering clean water. So you reverse the polarity, and adsorbed ions are rejected into water, which causes the reject stream. So by cycling rejection and production, you get clean water. And you create assemblies of this kind. In the laboratory, we test several materials. So we have built a company on this called the Innovative Deionization Company. Today, these technologies are put with solar on the coastal regions. Unfortunately, this technology is energy efficient. It is efficient in water rejection, but it is capital intensive, a little more than reverse osmosis today. But it is being implemented in the form of water kiosks. But material story is expanding. So two-dimensional materials, you can drill holes in this MOS2, nanoscale holes. So when you drill nanoscale holes, we found that you can drill holes of 3-4 nanometers, but you look at those holes in detail, you find that these are molybdenum-rich holes. When these holes are molybdenum-rich, if you irradiate these materials with sunlight, visible light, you create reactive oxygen species, and they destroy bacteria. They also destroy viruses. So it is possible to construct a filtration column. Water goes up, anti-gravity. White light is illuminating this material, producing reactive oxygen species. Bacterial concentration goes down. So I've shown you this kind of a story of material science expanding into prototypes and being implemented in the field. And this is now becoming a reality across the world. While this is happening, there are many other exciting things in the nanoscale materials. So we work on Clathrite Hydrates. So these are water cages wherein molecules get trapped, like methane get trapped. And these are interesting materials for energy because methane is energy. And we work in this along with our colleagues. But globally, this hydrate is being utilized from a context of, or thought about from the context of hydrate-based desalination. If you take hydrate from the seabed, that is where most of the hydrates are, and you take to the hydrate to the shore, and you take methane out from that, and what is left behind is pure water. And that is both energy and water simultaneously. So this is being practiced at IIT Madras as well as at NUS Singapore. So while this is happening, there are a number of analytical devices being developed. So I'm showing you an example from another laboratory where electrochemistry is done with a cell phone. So we do this routinely today for several analytical sensors. Good thing with a cell phone is that you also have geotagging associated with it for entire range of elements on the periodic table. So as this is happening, the world is becoming so different today with advances in spectroscopy. Nanotechnology and nanomaterials is making spectrometers as big as this to something as small as this. This is a 4 millimeter thin spectrometer in the laboratory. This is being connected to cell phone. So you just shoot at a water outlet and measure spectra. And by comparing this with various kinds of analytics, you get water quality. What is being done today? Right around, the Jal Jeevan mission is monitoring water quality across the country. So we are participating in that endeavor. And here, for example, this is one cluster of installations in Haryana. And you see all of these clusters. And these clusters are monitoring water quality with one of our startups. And all of these water parameters, daily water supply, residual chlorine, pH, pressure, nitrate, TDS, and all of these. And look at how this is going to. This is going to create to a situation wherein we have the hydroinformatics for the whole country. And this effort is happening today, at least in some places, select villages, select localities. But the way it is expanding is fascinating. Looking at water quality in a state, Punjab, during this 2017 to 2020, over 12,000 water wells. We look at how water quality is changing. And you see that the arsenic is spreading from Amritsar all the way down in the past just about 3-4 years. There are many, many aspects, and I will not be spending time on this. Where is this taking us? This is taking us to a digital twin of water, along with hydroinformatics, along with another subject matter that we are pursuing on wastewater-based epidemiology. And that is going to allow us to explore water and its implications on health and economics. But all of this will become possible only with appropriate policy interventions. Look at this. A country which was having all these diverse varieties of cotton, the red cotton, the blue cotton, the green cotton, and the yellow cotton and all, we have only one variety of cotton today because that cotton could be dyed properly with any color. As a result, all the other natural cotton disappeared, but in that process, our rivers got polluted. Now you ask this question, is it good to go back to the cotton of the kind? Maybe. Is it good to go back to rice of the kind that we had? We had over 100,000 rice varieties at the time of independence. We have just 7,000 rice varieties today. And many of these rice varieties are submergence tolerant, salinity tolerant, and many others. And should we go to these? And from a larger perspective, you also ask this question, should you ever clean water at all? Why not we control the source itself, where contamination occurred? Why not we look at, instead of looking at contaminant removal, why not we look at sustainable chemistry for production? So there are several related topics. I know that I'm just about getting to the limit of my time. So therefore, I will not dwell on to this. But as I said, there is a cost of water in everything. And if you put that cost of water in everything, including detergents, Water will be different. Yamuna will be different if you have a national detergent policy which stipulates what detergent we should use. And there is data in everything. And water has to come to the central stage only with data and policy and appropriate technology. Let me close this lecture by saying where we should go to. I'll take you to just one point. Earlier, we talked about how much water will cost. Really, something like 0.1 paisa per liter. If that is what it is, you're producing hydrogen from that water. You're producing water using that energy, and hydrogen itself will produce water. So this whole cycle is going to be a water cycle. And in that process, the world will run. This is going to be the true circular world in which water will drive economy. And I started with Jules Verne's book. And in another book, Jules Verne asked this question, hey, what will you run this vehicle automobile with? That vehicle you will run this automobile with will be water. Water will run that automobile. Water will run our water plants. Water will run our civilizations. On that note, we have built a new center called the International Center for Clean Water, where anybody can come and build a water technology and take that water technology with them. There's a 22,000 research laboratory at IIT Madras Research Park, which is a 1.2 million square foot facility. And our science is done by our students, and many of them are owners of companies today. And several industries and governments have participated in this endeavor in building a water secure country. This has been possible because of our great institution, my dear directors, Bhaskar, the past director, and Kamakodi, the present director. Thank you very much. I'll be glad to take questions.
Thank you, Professor. There may be a couple of questions, etc. Professor Bhavesh will coordinate that.
Yeah. So thank you, Professor Pradeep, for enlightening us with your knowledge. So I think in chat box there is no question. So it seems that they really delighted. I still posted again also if any question, but there won't be any question in the chat box.
Okay. Chat, I see some chat there. It says, yeah, you have written whether there are questions. Yeah, I see that.
Yeah, sir, one question. Mr. Siddhar Singh here asked that can we use water for rocket launches?
Well, too ambitious a question. It is not water that is used, of course. It is going to be hydrogen that is going to be used and oxygen that is going to be taken. It's a matter of how overall weight balance is going to be. So nobody carries both hydrogen and oxygen. Of course, oxygen is also carried beyond when you get into space, of course. But initial interest in energy is going to be water as far as hydrogen as far as terrestrial space is concerned. Now you ask this question, should water be carried? Now water is carried to make hydrogen is going to be a difficult proposition because energy has to be produced on the rocket. Unless of course, water reacts with a material and produces hydrogen in the process. This is also being thought about. In fact, it is going back to Jules Verne in 1965. He asked all these very interesting questions. Anyway, it's interesting to look at them. But sum and substance of this is that carrying water as a fuel is certainly not the proposal. The proposal is to use water during transport, including in these automobiles that one is talking about. Always it is water is used elsewhere, produce hydrogen or hydrogen plus oxygen, store it and burn it.
Yeah. Thank you, sir. So another question was, what is the benefits of using fuels like petrol and diesel with ethanol?
Well, this is not something of my territory to answer this question. What will be the specific advantages of such fuels versus anything else? The fuel of that kind and hydrogen are really not comparable. Kinetics of hydrogen combustion is super fast. Temperature is very high. So really, you are not comparing these two. At one point in time, people used petroleum because that was the only source available. Look at the civilization in the past 200 years. Hydrogen came in just very recently as a possibility. There is no material with that much of energy density for the past nearly, let us say, 180 years other than petroleum. Hydrogen came in much later. That itself is being intensely researched upon today. Is this the best way to produce hydrogen? Our over potentials are still substantial. We are not energy efficient in that process. So there is much more to be done as far as hydrogen production is concerned. So coming to your question as to why at all we should use petroleum-based fuels is just because we don't have other fuels now. Think about this. If you are all, assuming that you are a student, if you were to come up with the best possible water technology using solar hydrogen, who will anyway go for petroleum or coal-based energy? Thank you.
Yeah. Yeah. So the third question was, why is water the universal solvent?
Water is a universal solvent just because water exhibits every possible kind of chemical interaction. On the one side, it is in a position to interact with polar solutes. The other side, it is in a position to engulf even things like methane and carry with it. You can dissolve many of the gases with it. The water exhibits a multitude of properties quite different from normal solvents. This is to a many, you can't always explain several of these unusual properties of water. Therefore, you call them unusual. It's easy to say why water dissolves HCl. Water dissolves polar molecules. It is difficult to say why water is used for every possible industrial application. Now, you may explain it with hydrophilicity, hydrophobicity, cavity effects, hydrogen bonding, name it. So many of these terms, but the bottom line is that many of these unusual properties are still not fully understood at a molecular level.
Thank you, sir. The other question is grey water management system is appropriate method to reuse the water?
Grey water management is in the country, not only in our country, globally, there is a whole lot of innovation has to happen in this. Now, reuse itself is very culture dependent. Reuse is decided by energy. Reuse is decided by the kind of water stresses we are faced with. Reuse in our country is not really an interesting issue, important issue, because there are these cultural barriers. Reuse is used only in the context of limited utilization. There, reuse is intensely practiced. Now you ask this question, should greywater management system be appropriate for every reuse? Maybe. I think we are in our institutions should start, becoming 100%, utilizing 100% recycling. And we have to show these examples. Communities have to show these examples. Now, where are we going really? I mean, we work with a number of industries. We do recycling, we greywater recycling we do, but ultimately everything is going for watering. Everything is going for gardening. Very little is going for really reusing water for the processes water can be used for. Can we start reusing water for drinking? This is where we have to invest more and more technologies. This is where we have to show our way. Is it possible to connect our sewage to a drinking water pipeline through a process? These institutions have to demonstrate. Now, there are many examples globally, but we don't demonstrate it adequately for the community to accept it.
Thank you, sir. Thank you for answering queries of the students.
Thank you. Thank you, Professor, for such an informative lecture.
Thank you. Thank you, Apurva.
So thank you, Professor Pradeep, for a very comprehensive coverage of a very important topic for a developing country, especially a country like India. The science that covers from the hydraulic cycle to chemistry to chemical engineering to the entire gamut of biological issues, the flora, fauna, ecology. I think your talk was very comprehensive in terms of its coverage. And from that talk, one could see that there are lots and important decisions, maybe some at the policy level, that a country like India needs to take to be able to ensure that the benefit of science is actually reaped by the country. Whether in terms of clean water, whether in terms of availability of water. I think it is not only a matter of making right investments, it is also a question of making the right decisions at the right time so that we can use whatever knowledge we have up till now. Thank you for this wonderful Science Day lecture. On this occasion, I would also like to share a few thoughts of mine on the importance and on the reasons for the celebration of Science Day and how we use this occasion. We all know that this is a historical day for our country, and so naturally it's a cause for celebration, but it is also an opportunity to drive home a few points which we need very earnestly. And today is the occasion to understand 2-3 things very clearly. First is that what is science? I think this is a favorite topic that I often broach on Science Day, because sometimes during our school education, or because of the unequal opportunities that exist in different disciplines, we do not get the right perspective of what is science. Science is not only physics, science is not only chemistry, science is not only geology, science is not only geophysics, science is not only earth sciences. I think science is all pervasive. It is very difficult to find a body of knowledge which is not using science in some form? Well, it is true that experimental science is different. It's true that data science is different. But what is science? Science is something that is also used in, for example, economics. Science is also used, for example, in when we talk about computer science. When we talk about Bhatnagar Award every year, I think many of you would have noticed that it is called the category of engineering sciences. So the point is that it is an occasion to realize that there is a continuum of these disciplines. These are not segregated baskets or silos within which the disciplines exist, but this is a continuum. And when science becomes engineering, or when engineering becomes science, that is not clear in this continuum. It is not possible to do science without engineering. It is not possible to do engineering without science. So they are meshed within each other. They feed each other. They compose a continuum, and they are very important. In fact, one favorite thing that I often say is that go to the list of Nobel Prize winners in physics or chemistry, or even in other disciplines, and you will see that some of them would have engineered some of the best equipments. The experimental setup that they would have devised to be able to demonstrate the science would be the best engineering possible. And similarly, if you go to an engineering department, you will see that the best publications, the best papers come out of those labs which are able to distill the engineering, bring it to an abstract level so that it becomes science, which is all pervasive, which is all true. So today is a time to bow our heads that if we have to understand nature, if we have to understand human civilization, if we want to advance human civilization, this cannot remain a lip service. We must realize the fundamental nature of science. We must realize the important place that science occupies. Second point that I want to make, and this is probably a new point for many of you who may have heard me on Science Day. This is the point about the Constitution of India. We all know that this document is a very living document, a very comprehensive document, which was deliberated over several years, and then we got this Constitution of India. And it provides methods of amendments, it provides methods for doing different things. During one of these constitutional amendments, a very important thing was added in the mid-70s. We normally talk that I have a freedom of speech, I have a freedom of life, I have a freedom to educate myself, I have a freedom to propagate my beliefs. Very, very true. There are a list of fundamental rights as defined in the Constitution. Similarly, there is a list of fundamental duties. And one of the most important fundamental duty for all Indians is to develop and inculcate scientific temper. Today is a day when we must take a resolve that whenever we are given data which is contrary to whatever beliefs we hold, we must be willing to bow to that data and accept the truth that the data shows. We should not be very rigid in terms of our thinking, in terms of our thoughts, because science teaches us to respect whatever is the evidence, scientific evidence. If an electrical circuit is showing a voltage which is coming different from whatever computations that I have done, I must be willing to look at the calculations, I must be willing to redo my analysis, I must be willing to redo my science and not just ignore the data. That is scientific temper. Similarly, if somebody makes an argument which is based on data or experimental evidence, I should be willing to take it seriously. And if it requires a change in my thought process, if it requires a change in my beliefs, if it requires that something that I hold very dear to my heart needs to be changed because it is not true, or maybe it was true till now, but now in the face of this evidence, it cannot be considered true anymore, I should be willing to review and change. That is scientific temper. I think today is a day that we must resolve that we must not only pay lip service to scientific temper, but if we start practicing it, the quality of our research will improve. The quality of the problems that we define will improve. And we will be more evidence-based, more experimental-based, more data-based, more simulation-based, rather than being belief-based, rather than being hearsay-based. So with these words, I would like to congratulate our Academic Affairs Office for having done this Science Day function very carefully, very meticulously, having gone through an exercise of carefully selecting the speaker. Professor Pradeep has done a wonderful job in terms of selecting a good topic and giving a comprehensive lecture. And our school children who are part of this Roorkee town, this is a good time to connect with them. This is a good day to connect with them. They have also participated in various activities. Hopefully those activities would inspire them to take up science as a career, would inspire them to become true researchers, would inspire them to try and use science to solve the problems of our country, and we have lots and lots of problems to solve. That is the motivation with which IIT Roorkee does these events. I think this is a wonderful tradition. We must continue this tradition of involving school children. I congratulate all the winners of the various prizes, and I hope that we will see greater participation in the years to come from the school children. It is a pity that in 1921 and 22 we are holding this virtual function. Otherwise, if it had been a physical function, then we could have seen the school children and their teachers coming to the campus, and we could have given the awards. That would have given a very entirely different kind of feeling. Anyway, I'm happy that it has still been done, and it has been done properly, carefully, and completely. So thanks to the Academic Affairs Office. I think, thank you very much for giving me an opportunity to speak on this occasion.
Thank you, Professor Chaturvedi, for the motivational words. So now we have with us various school children personally connected to us. We have a very small, very brief prize distribution ceremony. I'm requesting Mazariti to coordinate.
Thank you, sir. So now is the moment to announce the winners for various events which were conducted by IIT Roorkee in virtual mode. First event was debate competition, which was held under two categories. Under category 1, we had invited children from the Roorkee schools between standard 9th and 12th. So the winner of this competition under category 1 is Montfort Senior Secondary School. That comes at first prize, Avantika Tyagi and Keshav Singh. First runner-up is Kendriya Vidyalaya number 1, Devansh Gupta and Tejas Tyagi from class 9th and 12th respectively. We have a tie at second runner-up position. So second runner-up, Sarvagya Public School, Roorkee, Varnika Bharlia and Richa Sharma from class 12. Second runner-up, Mount Litra Z School, Mahi Singh and Anushka Rana from class 10th. The committee also decided to award consolation prize to ABN Adarsh Bal Niketan Senior Secondary School, Amar Kayan and Aishwarya. Kendriya Vidyalaya number 2, Roorkee, Mahek Sharma, Radha Pandey for consolation prize. Second category for debate, wherein students of class 6 to 8 were awarded, participated and awarded. So first prize again goes to Montfort School, Roorkee, Rupayan Ghosh and Isha Tyagi. First runner-up, Adarsh Bal Niketan Senior Secondary School, Upendra Singh and Shrishti. Second runner-up to Kendriya Vidyalaya number 1, Roorkee, Tanvi and Kavyan Singh Kanyal. Second event was quiz competition, wherein 8 schools participated. So first prize here once again goes to Montfort School, Roorkee, and participants were Anishka Tayal, Sambhav Singhal, Manav Sachdeva and Yuvraj Singh. They are tied with 3 schools at first runner-up position. So first runner-up goes to Adarsh Bal Niketan Senior Secondary School. Participants were Ayush Tayal, Rakshak, Sadhana Yadav and Ishant Puri. First runner-up again to Mount Litra Z School, Kartikya Kulkshetra, Abhyuday Narayan, Shavez Alam, and Pranjal Raj. First runner-up, Army Public School number 1, Roorkee. Participants were Myra Raj, Karan Singh, Siddharth Singh, and Shuyog Nautiyal. The second runner-up goes to Kendriya Vidyalaya number 2, Roorkee, Mohammad Sajid Siddiqui, Kuldeep Bishnoi, Avni Tyagi, and Madhu. So heartiest congratulations to all our winners and our participants.
Congratulations.
With this, I request Professor Bhaja to take over the forum, please. Thank you.
Yeah, so I am Bhavesh Valja from Academic Affairs Office to present the vote of thanks on today's occasion of the National Science Day Celebration 2022. I would like to thank our respected chief guest and the speaker of the event, Professor Pradeep, Institute Professor, Indian Institute of Technology, Madras, Chennai, for sparing his valuable time and enlightening us with his knowledge. I firmly believe that today's lecture gave deep insights into the topic science, technology and innovation for sustainable clean water, and also inspired young minds present in this event. On behalf of the Academic Affairs Office, I would like to thank my profound gratitude to our Honorable Director, Professor Ajit Kumar Chaturvedi, for his constant support and encouragement. I would like to thank Professor Sandeep Banerjee, Mathematics, Professor Sriram Yadav, Bioscience and Biotechnology, Professor Himanshu Fulera, Physics, Professor Debasis Banerjee, Chemistry, for their contribution by conducting an online science quiz competition on 17th February 2022. I would also like to thank Professor Kaushik Ghosh, Chemistry, Professor Harsh Chauhan, Biotechnology, Professor Ravindra Pandey, Chemistry, Professor Pawan from Chemistry, and Professor Sachin Srivastava from Physics, and Professor B. Bhattacharya from Earth Science, along with Professor E. Gyanmani, Chemistry, for taking pain in conducting online debate competition on 21st January 2022. I am also thankful to head of the departments of Bioscience and Bioengineering, Chemistry, Earth Sciences, Mathematics, Physics, and ICC for giving their support and valuable suggestions. I am happy to express vote of thanks to all faculty members, students, guests, and students of schools of Roorkee who have made this celebration a grand success. With a special thanks to Almighty, I once again thank you all for your cordial cooperation. Thank you very much.
Thank you, Professor Pradeep. Thank you.
Thank you very much. Thank you very much.